Welcome to RamZland. Today I want to tell you the difference between ferro, para, and diamagnetism. Check it out. If you've ever made a temporary magnet, then you've already learned about ferromagnetism. This happens with metals like nickel, iron, and cobalt. When an external magnetic field comes along, it aligns the particles inside that metal and it becomes a temporary magnet. Even after you remove the external magnetic field, the metal maintains its alignment and still attracts other metals with iron, like this paper clip. It's still stuck to the screwdriver even after I remove the neodymium magnet. Diamagnetism is most of the elements on the periodic table. So in the case of copper, for instance, this is when a metal has no unbonded electrons. So all the electrons are traveling in pairs in their orbital. And when that happens, it repels magnetic fields, but it's not attracted to magnetic fields. So this copper plate down here, it's not attracted at all to my neodymium magnet. It repels the magnetic field. So when I drop it through here, you'll see that it actually moves very slowly. So I'll do it from above. So I'm going to drop it through. You'll see how slowly it moves. A fun example of diamagnetism is bismuth boats. Here's a piece of bismuth that's floating on some styrofoam. When I take my strong neodymium magnet and I get close, you'll see that the bismuth is repelled by the neodymium magnet and floats away. In this example, I have a piece of glass. It's diamagnetic. It keeps resisting the magnetic field that's surrounding it by the variable gap magnet. It'll keep pushing away and resisting that magnetic field because it has no unpaired electrons. Here's a piece of aluminum. It's paramagnetic because it has a few electrons that are unpaired. And that means that they can realign themselves with the magnetic field that surrounds them. So even if I spin it, it will realign its particles with the magnetic field that surrounds it because it's paramagnetic. It has a few electrons that are unpaired in their orbitals. And those electrons are able to realign themselves with the magnetic field that's caused by the variable gap magnet. Here's a pendulum that's made of aluminum. Again, aluminum is paramagnetic because it has some unpaired electrons that can reorientate themselves in the magnetic field. Paramagnets tend to turn toward a magnetic field. So when I release the pendulum, the magnetic field dampens its movement. This is what the pendulum would do without the variable gap magnet. It would swing freely. But when I add the magnetic field, the aluminum has electrons that reorientate themselves with the magnetic field, and the pendulum slows down very quickly. That's because aluminum is a paramagnet. I hope you enjoyed this edition of RamZland. Big shout out to Montana Bismuth that provided these awesome samples of bismuth for today's lesson. Remember, paramagnetism has one unbonded electron. It turns toward a magnetic field. Whereas diamagnetism has no unbonded electrons. Like in the case of copper, it turns away from a magnetic field. Of course, ferromagnetism, that's when you have a lot of unpaired electrons and you can actually align the domains of the metal so it can be a temporary magnet even after you remove the external magnetic field, as in the case of that screwdriver. I hope you enjoyed today's edition of RamZland, and I'll see you next time.